Hey guys, it's Mr. Chemistry here. Today I'll be going over the gas laws so that we can be prepared for this test that's coming up. Okay, so let's begin up top with the gas laws review, starting with the three laws. Boyle's, which relates pressure and volume together, while the temperature is held constant. Now, remember, if a variable is held constant, it just simply means that it does not change throughout the experiment, okay? All right, so moving on to Gay-Lussac's law, notice that volume is not part of this equation only because volume stays the same, which you can infer, you can assume that the reaction takes place in the same container, okay? Same rigid, I should say, container that does not change sizes, okay? So notice pressure and temperature are related. And moving on to the Charles's law, which we have volume and temperature and how they reflect of each other over time while pressure is held constant. Okay, so I'm going to add one more thing to this actually in blue. Boyle's law, this is going to be an example of an indirect relationship, okay? Which simply means that if one variable goes up, the other one will go down, okay? Vice versa, if one goes down first, then the other variable will go up. That's what an indirect relationship is, okay? Now, what about the two other gas laws, Gay-Lussac's and Charles's law? These two are great examples of when variables are directly related, which, do that right? Direct, which simply means that they as in two both variables will go up at the same time or they will go down at the same time, okay? So please know the difference between the direct and indirect relationships, okay? Moving on forward, we are given the pressure values. These are simply conversion factors, right? You can go from atmosphere to kilopascal to psi, vice versa. Okay, and standard temperature, we have 0 degrees Celsius, which is 273 Kelvin, right? So converting simply just means just plug in the degree Celsius that you know here and just add 273 to it and you'll be able to get your Kelvin. All right? So if you were to combine these together, that's when you have the STP condition, right? Which is short for standard temperature and pressure, which that is being 273 Kelvin or I should say and 1 atmosphere. Okay, so that's the standard temperature and pressure. All right, so let's get started. Number one, all the circled ones that I'm just going to run down, okay? 10 degrees Celsius to Kelvin. So what do I need to do here? 10 plus 273. That's all I have to do, right? Because I'm just plugging in 10 to that equation, which will get me at 283 Kelvin. Okay, that was pretty easy, right? So let's move on to part D. 815 kPa. What is that in PSI? So that would be an example of a unit conversion, which I'm going to go ahead and set the grid, right? Kilopascal. Let's go ahead and make this nice grid. Nothing's going down here. Now I'm trying to go from kPa to PSI, all right? Which means in order for us to cancel out the unit of kPa, I need to make sure that I have kPa unit down here. If you look up to the standard pressure values, what's the conversion factor of kPa? That is 101.3, right? Now, to go from to go to PSI, that's what I meant to say, we have to use 14.7 PSI, right? That's about it. The kPa units go away, and I'm just left with the numbers. Make sure you multiply everything across horizontally before dividing anything, okay? So here's what I'm doing in my calculator. 815 times 14.7. Okay, I get a really big number. I'm just going to divide that by 101.3. Okay, so that gets me approximately 118 psi. That's my unit, right? So 118. All right, that's it. Let's move on forward. Here's number 2. Identify what each of the following changes would do to the pressure. Okay, So let's see what happens. In a closed container, okay, that's really important as well, so that no gas is being leaked, right? And explain why. Okay, all right, let's get started. Some of the gas is let out, causing pressure to. Oh, okay. So, what exactly is pressure, guys? I need you to understand what pressure is. It's a type of force, right? And that is created from when gases are colliding or hitting against the walls of the container, right? So what that means is that if we have more gases hitting a lot more frequently against the walls, greater the force, greater the pressure is, right? So let's see. Let's say before, okay? Same container. I'm going to draw it twice. I'm going to duplicate that really quick. So that's going to be before and after, okay? I'm going to say I had, let's say, 1, 2, 3, 4, 5 gases just doing about their thing. And they had a X number of atmosphere pressure, okay? And if I were to remove a couple of particles, okay, and say, okay, I got 1, 2, 3 now instead of 5 gas particles, what do you think is going to happen to the pressure? Well, the pressure has to go down, right? Why? Because the number of collisions against the walls, right? I'm going to write that down. The number of collisions against the wall has gone down, right? Because there's only 3 versus 5, okay? To make things a little more obvious, why don't I go ahead and delete 2 more and say, you know what? I went from 5 particles to 1 particle. Obviously, 5 particles are going to hit the walls a lot more frequently, causing pressure to go up, right? But versus 1 gas particle, it's not going to hit as many times, right? That is why the pressure it must go down. Okay? All right, let's move on forward. The container size volume is decreased, causing pressure to, let's see. I'm going to take that same example. I'm just going to go ahead and duplicate this part right here. Except I'm just going to enlarge just a bit, okay? So let's say we had 5 gas particles inside this chamber, or I should say container, okay? And what happen over time? Let's say that I've reduced the size of the container while having the same 5 gas particles. What do you think is going to happen to the pressure? Well, let's try to get the story straight here. On the left side, I have a really big volume of a container, which means these gas particles, I mean, they are going to hit the walls, obviously. But just imagine being in a really, really big container. It's going to take some time for the gases to find the walls. You know what I mean? But now on the right side, we have a very small container, which means the gases are like, oh, this is a really small volume. This is a very small container. I'm able to find the walls a lot quickly, which means a lot more collisions against the walls, right? And we know if there's more collisions, that means more, what is that? Pressure, right? So let's see. The container size is decreased, causing the pressure to go up because more collisions. Okay? Now, the word collision, you need to be really careful here, guys, is that I'm only referring to the collisions against the walls, okay? Not from the collisions amongst themselves. That's not how pressure is created, okay? Pressure is only created from these gas particles hitting against the walls, all right? Just kind of keep that on the back of your head while you're doing these sort of free response questions, okay? And also, like me, drawing really helps, right? I mean, I'm a very visual person. Okay, so here we go. Part C. Temperature is increased, causing pressure to, okay, I'm going to use the same example again. All right, I'm going to go ahead and take this guy. Oh, I'm trying to duplicate this guy here. There you go. Okay, so let's say, see, we have this container at 25 degrees Celsius. Okay, room temperature. Now I'm going to go ahead and heat this up. I'm going to take the same thing again and I'm going to duplicate it on the right side. It's going to change, right? let's go ahead and draw in our little fire. Okay, and we're gonna heat it up to, let's say, I don't know, 60 degrees Celsius. Oh, it's quite hot, right? So what do you think the gas particles are going to behave this time? Okay, if I were to draw in the vectors, we talked about the vectors, right? The arrows being, the longer the length of the arrow, the faster, right? So at 25 degrees Celsius, I'm just gonna go ahead and draw in kind of shorter arrows, representing that the speed of these gas particles are not that fast. I mean, they're still moving, right? But it's just not fast, all right? But once I heat up the container, what's going to happen is that energy is going to be sent, right? Absorbed by these gas particles. And we know that if there's more energy, what can they do? They're going to be moving a lot faster, right? So let's go ahead and represent our new arrows. So I'm going to go ahead and draw. Okay, I'm being really obvious right now and drawing a lot, just longer arrows, something like that, okay? So that you can kind of visualize. I mean, it's pretty obvious that the arrows are longer, right? Which means they're moving a lot faster, which also means that the pressure has to go up, right? Because these gas particles on the right side, they're moving at a much faster speed, which means they're going to have an easier time finding the walls. So it will increase the frequency of these gas particles hitting against the walls, right? Which will bring up the pressure. Boom. Okay. All right, that's number 2. Okay, so the next 3 set of questions, I filled in the answer already because we've kind of talked about it already at the very start of this video. Okay, so Boyle, the first one, temperature. Which one of the 3 gas laws? Temperature is constant. That would be the Boyle's, which is this one, right? P2, V2. Do you see temperature anywhere? No. That means the temperature is held constant. That would be the Boyle's law. And the next one here, we have Gay-Lussac's law, which you know that volume is held constant, and that would be P1 T1 equals P2 T2. Notice that there's no volume anywhere, which means volume is held constant. That would be the Gay-Lussac's law, okay? Moving on to the third one, last but not least, pressure this time is held constant. And that would be V1 over T1, V2 over T2, where pressure is nowhere to be found. It doesn't mean that pressure doesn't exist, right? It's just that pressure is held constant throughout the experiment, which is the Charles's law. Okay? All right, so I'm going to be skipping over these questions, and I'm going to do some calculations now, finally. Great. Okay, so for the rest of the problems, we got 4 parts. Wow. Part 1, write down your givens with PV or T and their corresponding units. 2, write the equation you're using. Number 3, solve it, obviously. And number 4, box your final answer. And don't forget your units, right? No naked numbers. Let's give them some clothes. All right, so here's number 9. The gas is sealed. Rigid tin can is at a pressure of 3 atmosphere at 25 degrees Celsius. Wow. I'm like right off the bat, I'm giving 2 variables. So that's pressure is at 3 atmosphere. And what is my temperature? Is at 25 degrees Celsius. A quick note of reminder, guys. Anytime when you're using any of these gas laws, make sure you convert degrees Celsius to Kelvins at all times, okay? So let's go ahead and do that quickly. 273, you're adding to it, right? So that gets me at 298 Kelvin, okay? All right, so let's move on forward. A warning on a tin can tell the user not to store the can in a place where the temperature will exceed 52 degrees Celsius. What would the gas pressure the can be at 52 degrees Celsius? Okay, so here's change. So we know that these are the initial values, right? So P2 is what we're trying to find. It's the X, atmosphere. Okay, it's the missing variable. It tells us, right, what would the gas pressure be at 52? So we know that temperature has gone up, right? From 25 room temperature to 52 degrees Celsius. Okay, so 52 degrees Celsius. Now, can I use that 52 and just kind of plug it in into one of the gas laws? No can do, right? I just said you must convert all Celsiuses. Is that a thing? Celsiuses to kelvins, okay? So 273, let's go ahead and work that out. So that's 5, that's 325 Kelvin, okay? All right, so I'm not quite done here. That's just my variables. I've now done part 1 of this question, okay? So I'm just gonna clean that up a little bit. All right, so which one of the 3 gas laws would I have to use for this one? I have pressure, I have temperature, but volume is held constant, right? And therefore, I'm going to have to find the one that only has pressure and temperature in it, and that would be the Gay-Lussac law, which is P1 over T1 equals P2 over T2. All right, now it's just plug and chug. Simple stuff, right? Pressure, atmosphere, that's starting with 3 atmosphere over 298 is equal to, this is x, what we're trying to find, over 325. Okay? All right, now we're just going to have to cross multiply, right? So I'm going to go ahead and try this side first, the one that has x variable in it. So that's 298x, which is equal to, let's go with green for this one. Okay, so what's 325 times 2? Times 3, sorry. That's 975. Okay, all right, so how do we solve for x here? By dividing both sides by 298. Okay, and my x pressure is 298, 3.3 atmosphere. Done. Okay, 3.3 atmosphere. All right, so that's it for this question. Let's move on forward. Okay, so let's do 11. Excuse me. A sample of neon gas occupies a volume of 725 liters at 25 degrees Celsius. Okay, again, I know that it tells us that volume is 752. So volume, initial volume is 752 liters at 25 degrees Celsius, room temperature. Okay, so T1 is at 25 degrees Celsius. Now, again, notice that that's in degrees Celsius, which I'm going to have to convert that to Kelvin. 298 Kelvin, okay? What will the gas occupy? Okay, so we know that something's changing, right? And what volume? So we're trying to find what the final volume is. And when the temperature is, this time the temperature is lowered to 20 degrees Celsius. Okay, sweet. Just convert it, right? 273, add it. So that's 293 Kelvin. All right, so let's see. It also tells us that the pressure remains constant. Great. Pressure does not change over time. Okay, so which one of the 3 gas laws we're going to have to use this one? Find the one that has the 2 variables, volume and temperature, and that would be the Charles's law, right? Which tells us that volume 1, T1, is equal to V2 over T2. Now it's just plug and chug, right? Do I have all the units aligned? Let's see. Volume, liters to liters, good to go, right? Temperature, kelvins to Kelvin, we're good to go here. So V1, 752 over 298, which is equal to x over 293, okay? Same thing again, just cross multiply. 298x is equal to, that's a big one, 752 times 293. Wow, 220336. Okay, now divide both sides by 298, and I am left with, that's a big number, okay, 739.4 liters. Done. Okay, well that makes sense, right? Because This is Charles' law, which means that this is what kind of relationship does do the pressure and temperature have? They have a direct relationship, right? So notice that the temperature is going down, right? So 298 Kelvin to 293 Kelvin. Then volume is going to go down as well. Did it go down? Yes, indeed. That's how you can double check your work, right? By using the direct and indirect relationships, okay? All right, so that's 11. Let's move on forward. Okay, here's 13. Ralph had a helium balloon with the volume of 4.88 liters at 53 psi pressure. Okay, that's cool. So let's go and label these now. Volume is at 4.88 liters. Okay, and pressure, it's 53 psi. Okay, so we're now in a different unit. That is not a problem. Okay, if the volume is changed, okay, so volume is changed, right? We know that something's changing. So I'm going to go ahead and draw an arrow indicating that there's some sort of change going on. So volume to 3.15 liters. Okay, so now we're trying to find what the new pressure is, X. However, oh, that's a tricky one, would be the new pressure in ATM. Okay, so I see what they're trying to do here, trying to trick us, right? So take a look, guys. Pressure 1 is in terms of PSI. However, we want pressure 2 to be in terms of ATM. Do you know what that means? I'm going to have to convert this guy to ATM. All right, making sure that both pressure units are aligned. Otherwise, you're going to get a very wrong answer, and we don't want that, right? So let's go ahead and give that a go. All right, so 53 psi, just converting using the little grid, right? So now let's go ahead and scroll up a little bit and see what the conversion factor is going from psi to ATM. So let's go up, 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 all the way up. And here we go. So what's psi to ATM? Okay, so I'm going to use pink. I know it's getting a little messy. Stay with me, guys, okay? So here's 14.7, right? PSI going to 1 atmosphere. So that's what the conversion factor is, right? Every, like, 1 atmosphere, there's going to be 14.7 PSI. Vice versa. Every 14.7 PSI, there's going to be 1 atmosphere, okay? So let's go ahead and bring that down. So remember, 14.7 PSI to 1 atmosphere, okay? Here we go. 14.7 PSI, 1 ATM, okay? All right, so now I have the units aligned diagonally, right? So PSI, they both go away. I'm just left with atmosphere unit, which is exactly what I want. Okay, so let's go ahead and do the math here. 53 times 1. I mean, I really hope you're not putting that into your calculator. It's just 53 divided by 14.7. That gives me 3.6 ATM. Okay? So that's what it is. So let's go ahead and bring this to the side a little bit. Okay, so this is my initial pressure. How should I represent? Okay, right here. That's what it is, right? Okay, now everything is aligned, the units. Now I'm just gonna determine which one of the 3 gas laws that I'm gonna have to use, okay? So I got 2 variables that are changing, volume and pressure. Let's see, what is volume and pressure? That's going to be the Boyle's law, right? Which tells us that P1 V1 is equal to P2 V2. Just plug and chug from now on. Pressure 1, I got, I almost plugged in 53. 3.6 atmosphere, right? Times the volume being 4.88 equals pressure 2 is what I'm trying to find here, right? X times, what is it? 3.15? Yep. Okay. So how do I isolate this x on the right side? By dividing by 3.15 on both sides, right? These go away. And x is going to be, let's work out the math here, 3.6 times 4.88 divided by 3.15. Okay, so I got approximately 5.6 ATM. Done. Okay, so let's go ahead and double check our work here, guys. So volume has gone down while pressure has gone up. Does that sound right to you for Boyle's law? Yes, because Boyle's law in direct relationship, right? Which means if one goes up, the other comes down, vice versa. The volume has gone down, therefore the pressure will go up. And yes, it did. Yay. All right, so here's 15. Let's do a couple more questions. A sample of 25 liters of NH3 gas at 10 degrees Celsius is heated at constant pressure until it fills a volume of 50 liters. Okay, so let's go ahead and write a lot of these. Just let's sort them into their variables, okay? So 25 liters, that would be the volume, right? Volume 1 is at 25 liters, and the temperature is at 10 degrees Celsius. Okay, again, that is in degrees Celsius. I'm going to make sure to convert that. Add 273. 283 Kelvin is my initial temperature. Okay, and it changes, the conditions change, right? Until it fills a volume of 50 liters. So volume is going to double, it seems. 50 liters. What is my final temperature? That's the x, right? So let's see. Which one of the gas laws am I going to have to use for this one? I got volume and temperature. That would be the Charles's law, okay? Just going to shrink that in size a little bit. Wrote it too big. Okay, so that's V1 over T1 equals V2 over T2. Let's just plug and chug. Volume 1 is 25 liters, right? 25 divided by temperature 1, that's 283, equals 50 liters over x, the new temperature. All right, so let's go ahead and work this out. Cross multiply. 25 times x is simply 25x is equal to, what's the next one? 283 times 50. That gives me a really big number, and that's okay. Divided by 25 on both sides. 25s go away. All right, I'm just going to take this here a little bit. Running out of room. X is now equal to 566. And what's the unit for this one? What's the unit, guys? That's temperature, right? So I'm going to put my K next to it because that's my Kelvin. All right, so let's try to make sense of this a little bit. So this law, Charles's law, we know that it's a direct relationship, right? Which means if one goes up, the other will go up as well, right? Vice versa. So volume has gone up, right? From 25 to 50. And did the temperature also go up? Yes, it did. Boom. Okay, there's 15. Okay, so here's 18 now. Drawing of diagrams. Given the image below, assume a sample of gas is enclosed in the containers. Draw a picture of how the particles will behave as the volume of the container increases. Okay, so in the last column, list how the variables would change if the container changes as shown. Okay, well, let's see. So I'm going to go ahead and draw a few gas particles first, okay? Here's 1, 2, 3, 4. Okay, I'm going to do the same thing on the right. Well, before, I'm going to make sure that I draw in the arrows indicating how fast they're moving, right? So take a look, guys. First, I'm going to see that room temperature, 298 Kelvin, and also 298 Kelvin, which means the speed is not going to change, right? Because we're not lowering or we're not heating up temperature. So, I mean, the speed is going to be all the same. So the length of the arrow, I'm just going to draw kind of like short arrows because room temperature, I mean, they're not moving as fast as, versus when they're heated up. So something like this, something like this, something like this, okay? All right, now here's what I'm going to do. I'm actually going to duplicate the exact same thing See what I did there, right? And I'm going to just drag it to this side, right? Now let's go ahead and answer some of the questions we got going on here. Change in gas variables. Pressure. What happened to the pressure, guys? Okay. Before, when the container was a lot smaller, these gases had a pretty easy time, right? Finding the walls. So, which means the frequency of the collisions, the gas hitting the walls were pretty high. Okay. Versus on the right side, we have a really, really big container. Now, these same gas particles, they're going to have a much harder time finding the walls, right, of this container. That's why the frequency, the amount of times that these gas particles are hitting against the walls will decrease, right? Because it's so big. So the pressure has to go down because these gas particles are not hitting the walls as much as they did before, right? So that's how the pressure is going down. So volume has gone up. Okay, if you're thinking, wait, how did that go? Well, guys, look, the volume, we're talking about the volume of the container, right? So container went from small and it has expanded, increased, right? So naturally the volume is going to go up. Now, what about the temperature, guys? How do we represent temperature? Well, if you look, guys, it says 298 Kelvin, 298 Kelvin. Nothing's changed. That's why we're going to do like a little side arrow, right? Sideways arrow, indicating that temperature has remained constant throughout this experiment, right? And what about the number of moles, right? This N is the number of moles, okay? Which really just comes down to how many particles, right? Stay the same, okay? This, I mean, was there any mentioning of like, hey, there was a leak, a few gas particles escaped, or we've added more? No, there was not any mentioning of that, right? Which you can assume that the number of gas particles stayed constant throughout. That's why I'm going to go ahead and draw the sideway arrows again. Wow, those are terrible sideway arrows. But you get the point here, okay? So which gas law is demonstrated above? Well, let's see. Temperature is not part of it because it stayed constant. The number of moles stayed constant as well. So the only two variables that actually changed were pressure and volume. And if you look back to the gas laws, that's going to be the P1V1 equals P2V2, Boyle's law. Okay? All right. So write an explanation about the gas behavior inside the container based on the changing variables. Why do the variables change? Oh, I believe I just answered that question, right? Right? The thing about collisions, before small container, a lot more collisions against the walls, therefore high pressure. Now, new environment, much, much bigger container. Therefore, these gases, they have a pretty difficult time finding the walls of the container because it's so big. That's why they're not hitting the walls as much, as frequently as they did before, decreasing, lowering the pressure. Okay? I know, mouthful. All right, so let's go ahead and do some ideal gas law now. Finally, we're here, guys. We're almost done. PV equals nRT. Awesome thing about ideal gas law is that there's no like initial and final, okay? Because ideal gas law, it really just predicts. It predicts how gases behave under ideal conditions, okay? Now, a couple of things that you must remember, okay? Pressure always has to be in atmosphere. I'm going to write that down. Volume has to be in terms of liters. And N is moles. You know how to find moles, right? Sometimes a question might give you like grams of something. Make sure to convert that to moles using the molar mass. R is the gas constant, which is right here, 0.0821. And temperature must be in Kelvin as well. All right. Okay, so with that in mind, let's go ahead and do some of these questions now. 19. 1.7 mole. Okay, right off the bat, I know what mole is. Boom. Easy. Occupies a volume. Oh, okay. Volume of 60 liters at a temperature of 325 Kelvin. Wow. How nice. Okay. All right, so what is the pressure inside the container in atmosphere? pressure is what we're trying to find, and we know what R is, right? So let's go ahead and solve for P here. I'm going to go and write down the PV equals nRT. And what variable are we trying to solve for here? Pressure, which means we want pressure to be by itself on one side, which means I'm going to have to get rid of this V here. Just move it over, right? V's go away. Therefore, I got P equals nRT all over volume. Plug and chug. Now, let's make sure everything is in its corresponding units, right? Let's see. N, is that in terms of moles? Yes, it is. So let's go ahead and plug that in. Now, R, oh, okay, so that's just a constant, 0.0821, okay? Oh, guys, that's a typo. Nope, not good. This should be 0.0821, okay? Sorry about that. Let's move on. Temperature, what do we have here? 325 Kelvin, right? Now, should it be in Kelvin? It should absolutely. Sometimes it'll try to trick you by giving you Celsius. You know what that means, right? Convert to Kelvins. Okay, 325 all over volume. Is that in liters? Yes, it is. So I can go ahead and use that. Just plug all that in, okay? Wow, that's a big 1.7 times 0.0821 times 325 divided by 60. Okay, that gets me at 0.76 ATM. Dunsies. Okay, that was pretty simple, right, guys? Okay, let's move on forward. Let's see, one last question. All right, we're here. We're finally here, guys. Well done. There are 3.24 moles of C3H8. Okay, so that's N, right? 3.24 moles on a 29.6 degrees Celsius summer day. Well, okay, temperature, 29.6 degrees Celsius. Now, I'm going to stop myself really quick. Okay, that's in degrees Celsius. No bueno, not good, right? I'm going to go ahead and convert that to kelvins by adding 273 to it. Okay, 273 plus 29.6. Okay, I got 302.6 Kelvin. All right, let's move on forward. With a pressure of 253 kPa is built up, what must the volume of the tank be? Okay, so we're trying to find what volume here is, right? Now, I'm going to stop myself once again. Before I change any variables around and plug and chug, I'm going to make sure all the units are good. Moles is good, kelvins is good, kPa is not good. Remember, pressure should always be in atmosphere when you're using this ideal gas law. Okay, so how do we convert from kPa to 1 atmosphere? Well, you are given, let's see, let's go up here all the way to the top. Wow, it's really messy up here, right, guys? Okay, gonna get rid of that. So I'm trying to go from kPa to atmosphere, right? Because we want everything being pressure in terms of atmosphere. So to go from kPa to atmosphere, boom, that's it. 101.3 kPa is equal to 1 atmosphere. All right, so remember that, guys. 101.3 to 1. Scroll all the way to the bottom again. Here we go. Let's move this down a little bit because I need to convert. All right, let's make that beautiful grid. Here we go, back at it. kPa should go down here so that the units are aligned horizontally, right? 101.3 kPa is equal to 1 ATM, which is exactly what we're trying to find. All right, let's do some divisions, right? 253 divided by 101.3. I got 4.5 atmosphere. Oh, that's not 4. Don't know how to read numbers. 2.5 ATM is the pressure that's given to us, okay? We're good to go now, guys, okay? We're good. Everything is converted, and all we need to do now is solve for V. Let's do it. PV equals nRT. Okay, since we're trying to solve for V, I have to get rid of P, right? So the P's go away, just left with, yeah, that's what it is. Yeah, or I'll just rewrite it. V equals nRT all over P. All right, all I have to do now is just plug and chug. 3.24 moles times 0.0821 times temperature is 302.6. Sorry, running out of room here, guys. And all over 2.5. Okay, let's go ahead and put that into our calculator. 3.24 times 0.0821 times 302.6. Okay, all over 2.5, which gives me 32.2, and that's volume. Therefore, it has to be liters. Okay? All right, guys, I hope that was helpful. Study well and let's do well on the test. See ya.